Hello everyone, my name is SeungJeh from Triple I Excel Lab. Today I'll be presenting the paper titled Mamba, Linear Time Sequence Modeling with Selective State Spaces. This work was published at Conference on Language Model 2024. As many of you might know, Mamba is the model that truly challenged the Transformers' long-standing monopoly in NLP. So I hope today's talk gives you a good understanding of its core concept. Let's start with the domain and background. Mamba is designed to serve as a general sequence model backbone across various modalities. To understanding why Mamba was developed, we first need to briefly look at the limitations of the two dominant architectures in this field, transformers and RNNs. Transformers are currently the universe standard because of their exponential performance in routing information. However, they suffer from a fundamental drawback: quadratic computational scaling with respect to sequence length. The longer the sequence, the behavior and the heavier and slower they become, which makes them highly inefficient for long contexts. On the other hand, traditional RNN process data in linear time and require only constant memory, making them highly efficient. But they have a critical weakness: their effectiveness is heavily limited by how well they compress context into a finished state. As sequences get longer, they struggle to remember past information due to issues like gradient vanishing. Mamba solves this exact dilemma, aiming to achieve the modeling power of transformers while scaling linearly in sequence length. Now let's dive into the state space model, SSM for short. SSM is the foundational building block of Mamba. Originally, SSM are mathematical models from classical control theory used to describe continuous physical systems. However, they couldn't be directly applied to deep learning due to several computational bottlenecks. This completely changed with the development of the structured SSM, which finally made it practical and efficient for deep learning. So for the next few slides, I will explain the core concept of SSM based on this structured framework. Let's look at the core dynamics of an SSM. The system is governed by four key parameters: A, B, C, and delta. Let's first focus on the continuous system, which is defined by simple differential equation. Metric A dictates how the past hidden state transitions to the current state, essentially acting as the memory. Matrix B projects the incoming input into this hidden state. Finally, matrix C projects this internal hidden state to generate the actual output. In short, the state is constantly updated by combining the past memory through A and the new information through B. However, since deep learning operates on discrete tokens like text, we cannot use these continuous equations directly. This is where the parameter delta comes in. Delta acts as a step size to describe the continuous system into discrete metrics, converting A and B into A bar and B bar. You can think of it like sampling a continuous analog audio signal into a discrete digital file. Once discretized, the model can efficiently process the sequence data step by step. Naturally, this discrete system is computed using a recurrence method, processing one step at a time, just like on RNN. However, there is a mathematical trick. Because the metrics A, B, and C remain constant over time in this SSM, the entire sequential process can be mathematically unrolled and computed as a single convolution. This is a huge advantage. It means that during training, we do not have to wait for the previous step to finish. We can process the entire input sequence in parallel. Furthermore, by utilizing the fast Fourier transform to compute this convolution, we can achieve near linear computational complexity. As a result, training becomes fast and efficient. Now let's look at the structured part of the structured SSM. As I mentioned earlier, traditional RNN struggle with long-term memory due to the gradient vanishing problem. Structured SSM solved this mathematically using a theory called HIPPO. HIPPO carefully initializes the matrix A to optionally compress and memorize continuous signals. This allows the memory to preserve long-term memory without losing past information. Additionally, this architecture introduces a highly optimized structure, the diagonal matrix. Instead of computing a massive n by n matrix, it reduces it to a simple diagonal matrix of size n. This structure breakthrough drastically reduces the computation cost, allowing the model to handle much longer input sequences with incredible efficiency. If you want to dive deeper into these mathematically derived structures, you can find the details in the original Hippo paper. However, I must warn you that the paper is notoriously math-heavy and difficult, so if your main goal is simply to understand and utilize Mamba, I highly recommend just taking the intuition we discussed here and moving on. Now, despite these mathematical breakthroughs, traditional SSMs face a critical bottleneck. They are linear time invariant systems. What this means is that the model applies the exact same A, B, and C metrics to every single input token. It is not input dependent. Because of this, the model fundamentally lacks the ability to selectively focus on important information or ignore irrelevant data based on input. Consequently, it lacks the context-aware ability that makes transformers so powerful. In NLP tests, for instance, a model absolutely must be able to filter out useless noise tokens and perform in-context learning. Since the traditional linear time invariant SSM cannot do this effectively, its accuracy and efficiency in language model drop significantly compared to transformer. This exact limitations brings us to the core of this paper, Mamba. To overcome the shortcomings of traditional linear time invariant systems, Mamba builds upon the structured SSM by introducing two groundbreaking components, a selective algorithm and a hardware-aware algorithm. By integrating these two innovations, Mamba achieves something remarkable. It maintains the highly efficient linear time complexity of RNN while simultaneously enable efficient information exchange between tokens. Ultimately, this allows Mamba to achieve a performance that strongly rivals and sometimes even exceeds that of attention-based transformer. Let's dive into the first of these two key innovations, the selective algorithm. As we discussed earlier, traditional SSMs suffer from being linear time invariant. This new algorithm completely shifts the model from a linear time invariant system to a linear time varying system. The parameters b, c, and delta are no longer fixed. Instead, they are generated as the output of linear layers applied directly to the input token. So they become dynamically dependent on the data itself. Even though the core continuous matrix A remains fixed, because delta is now time varying and depends on the input. The resulting discrete matrix A bar fundamentally becomes time varying as well. Thanks to this linear time varying property, the model's matrix now changed for every single token. This grants Mamba the exact ability it was missing. It can now dynamically filter out irrelevant noise and selectively process information, effectively solving the content-based reasoning problem. However, this selective algorithm introduces a massive computational challenge. Because the system is no longer linear time invariant, we can no longer use the fast convolution operations. We must revert to calculating step by step using the recurrence method. This creates a fatal bottleneck in the GPU's memory bandwidth. At every single step, a massive hidden state tensor must be continuously written to and read from the GPU's relatively rel- slow, high, high bandwidth memory (HBM). To solve this, Mamba introduces its second core innovation, the hardware-aware algorithm. This algorithm maintains the linear time complexity of the recurrence method, but completely resolves the memory I/O bottleneck. As a result, it achieves incredibly fast training and inference speeds, matching the parallel processing power of GPUs. This hardware-aware algorithm is powered by three key techniques. First is kernel fusion and SRAM utilization. Instead of constantly moving large data back and forth from the slow HBM, Mamba brings the parameters into the ultra-fast SRAM on the GPU. It fuses the operations, performs them all at once in the SRAM, and only writes the final output back to the HBM. This drastically reduces memory access time. Second is the parallel scan. Even though recurrence is inherently sequential, Mamba applies a work-efficient parallel scan algorithm to maximize the GPU's parallel processing capabilities. Third is recomputation for backpropagation. To prevent memory from overflowing during training, Mamba does not save the massive intermediate stage. Instead, it simply recomputes them during the backward pass. This might sound slower, but because it saves so much memory I/O time, it is actually much faster. Now let's take a closer look at the internal structure of the Mamba block. When an input enters the uh, When an input enters the block, it splits into two distinct paths: the main branch, where the selective SSM is applied, and the gating branch, which evaluates the importance of the input information. Let's follow the main branch first. The input passes through a projection layer to expand its representational capacity. Next, it goes through a 1D convolution layer to capture local short-term relationships between tokens, followed by a CLU activation function. After this, a linear layer generates the time-varying parameters B, C, and delta. These parameters, along with the matrix A, are then used to perform the core selective SSM operation. The output from this SSM is then multiplied by the activation from the gating branch. Finally, this combined result passes through one last projection layer to produce the final output of the Mamba block. To summarize, Mamba successfully optimized both its internal logic and its overall architecture. By enabling efficient information exchange between tokens, it achieves performance that truly rivals transformers. At the same time, its linear time complexity scaling allows it to handle massively longer input sequence that attention-based models struggle with. Before I finish the presentation, I'd like to briefly mention where the field is heading next. Recently, we are seeing state-of-the-art performance from models like Mamba 2, which further pushes computational efficiency, as well as hybrid architectures that combine Mamba with attention or mixture of expert layers like Jamba and Samba. I firmly believe that if you understand and leverage this Mamba-based architecture well, it will open up many exciting opportunities for your own future research. Thank you for watching.